Welcome everyone to the Tao Salon of Statistics. Today, we're not just learning a method, we're exploring an elegant way, a Tao, if you will, of finding the real story hidden in the chaos of data. So let's start with the big question, the one that's at the heart of pretty much everything. Is that new marketing campaign really working, or was it just a good week? Did that new diet plan actually make a difference, or is the weight loss just, well, random fluctuation?
And to help us find our way, we're going to lean on a really powerful tool called analysis of variance, or as most people call it, ANOVA. Now, I know, it sounds a bit technical, but at its core, it's a beautifully simple philosophy for seeing what truly matters.
So the first step in this way is to get one thing straight. All the differences, all the variation we see in our data, it's not all the same. The absolute genius of ANOVA is that it helps us partition, or you could say cleanly separate, all that variation into different sources. Okay, so let's picture a study with, say, 4 different diets. At the end of it, you've just got this big pool of results, right? Some people lost a ton of weight, some lost a little, maybe some even gained a bit. That whole messy collection of outcomes is what we call our total variability. It's the whole puzzle we're trying to explain. And this is where the magic really happens. ANOVA takes that total variability and splits it neatly into 2 buckets. On one side, you have the signal. These are the differences between the diet groups. This is the variation we hope is explained by our experiment. And on the other side, we have the noise. This is just the random variation within each of those diet groups. It's the stuff we can't explain, just life, luck, individual differences. All right, so we've separated our signal from our noise. But so what? How do we know if that signal is actually meaningful? Well, that's where the FStatistic comes in. It's a single, powerful number that basically tells us the whole story.
This is the crucial question, isn't it? I mean, if the difference between the diets is just a tiny whisper, but the random noise within each group is a roaring crowd, our signal just gets drowned out. We need a way to measure the relationship between the two.
And the solution is, honestly, just beautiful in its simplicity. The FStatistic. It is nothing more than a ratio. We just take the amount of variation explained by our experiment, the signal, and we divide it by the amount of random, unexplained variation, the noise. That's it.
So going back to our diet study, the variation between the groups, our signal, was calculated to be 32.4. And the random variation within the groups, our noise, that was much, much smaller. It came out to just 5.3. So when you do the math, 32.4 divided by 5.3, you get an FStatistic of 6.1. What that means in plain English is that the pattern we saw from the different diets is more than 6 times stronger than all that background static. Now that sounds pretty significant, doesn't it? But in statistics, sounds pretty significant just doesn't cut it. We need a final verdict. We need to know the probability that we were just fooled by randomness. And this brings us to the final piece of our puzzle, the p-value. This is the question every good skeptic asks. A signal 6 times stronger than the noise is great, but couldn't we have just gotten lucky? Is it possible that a result that strong could have happened purely by chance, even if the diets actually had no difference at all? The absolute best way to think about the p-value is as a surprisometer. It answers a very specific, kind of backward question. If we assume for a moment that the diets are all identical, that the true signal is 0, what's the probability of getting a result as strong as the one we saw, or maybe even stronger? Well, for our diet study, the p-value came out to 0.0011. Let's break that down. This means there's only a 0.11% chance, that's about 1 in 1,000, of seeing such a strong signal if all the diets were actually the same. Our result isn't just a little surprising, it's extremely surprising. And because that chance is so incredibly low, we can confidently turn around and reject our starting assumption. We can say, you know what? The idea that the diets have no effect is probably wrong. We have strong statistical evidence that the signal is real. At least one of these diets is truly doing something different. Now, this whole thing isn't just some academic exercise. This 3-step way of thinking, partitioning the variance, checking the ratio, and then measuring our surprise, it's a seriously powerful strategy for making better decisions in just about any field. So let's just recap the Tao of ANOVA. It's 3 simple ideas. First, variance partitioning. You isolate the effect you're testing, the signal, from everything else, the noise. Second, the signal-to-noise ratio. You quantify just how much stronger your signal is. And third, probabilistic proof.
You measure how confident you should be in that result.
And you see this thinking-driving strategy everywhere. In business, you use variance partitioning to figure out if a new product feature is a real signal for engagement or if it's just random user noise. In marketing, that signal-to-noise ratio tells you precisely how much more effective campaign A was, so you know where to put your money. And that p-value? It gives you the confidence to launch a new package design, knowing the preference for it isn't just a random fluke.
So as we close our session at the Tao Salon, I'll leave you with this question to think about. In your work, in your life, what are the key signals you're really trying to detect? And what's the background noise that might be drowning them out? The way of ANOVA? It gives you a powerful lens to find out. Thanks so much for joining us.